Okay, everyone, welcome to Handmade Hero, day 31. This, of course, is the show where we program an entire game from scratch, live on the air. And, of course, the reason that we're doing this is because I think it's just a good idea for everyone to have the experience at least once of writing a game from start to finish so they know how absolutely everything works in the entire pipeline of a game. It's very empowering to do this because it means that you never have to be restricted again by something that someone else wrote. You can always choose to go write some portion of an engine or some portion of a library yourself, or even the whole thing yourself if you were so inclined. But it also means that even if you're just using things that other people wrote to build your games, you will be able to know how those things themselves work. And so that actually makes you a much better programmer as well, because you can do things like understand the performance implications of the things that you're doing. And that can help you even when you're using like an engine that somebody else wrote. So I think it's a great thing to do, and I think people have been enjoying it. And I have certainly been enjoying it. So with that in mind, I think it's a good time to go ahead and get started here. Let's see. If you are following along with the source code at home, which you can do on handmadehero.org, if you go to the pre-order button, if you've pre-ordered it, there should be a link that came to your email that you can click on and download the source code. I update it every night after we finish coding, and you can open up that link and you can download a zip file. Inside that zip file, there's a zip, like a sub-zip for every day. Since we're on day 31, you want to start with day 30. You always start with the previous day. So if you unzip day 30 into a directory and start coding in that directory, you will be exactly where I am today when I am starting, because that is the source code that I am starting with as well. Now, where we were when we stopped last week is we were actually at the point where we had our little yellow rectangle that we were basically using as a test for the player moving around a little gray and white rectangle, sort of blobby Tilemap placeholder, and we were just verifying that we could do some very basic things like move him around the tile map. We could have doors that he could walk out of, that sort of thing. And you know, nothing particularly fancy, but again, what we're trying to do here is explore the code a little bit and basically figure out what sorts of things we're going to want from our engine so that it supports the game that we're trying to make cleanly and doesn't involve, we want to basically avoid going and writing an engine without any knowledge of what we want it to do, because we'll probably liable to make a lot of bad decisions. So what we're basically doing here is trying to get down to what are the exact things that we need the engine to do and how we want them, how we want it to do them, so that we can then go implement the engine and do it in a nice, clean, concise way that does exactly what we want and that will be very convenient for us to use. So what we've gotten ourselves to at this point is a very basic thing where we can sort of do what we wanted to do with the tile map, and we can sort of check for collisions and do that sort of stuff in a very basic way. But there's a bunch of things that we should probably talk about here, and there's also a bunch of things that I want to sort of bring to your attention about it. Before I do that, I do want to talk about one thing briefly, because it had come up a little bit on the forums over the weekend, and I just wanted to sort of clarify some stuff for people, just in case they were concerned about this. So obviously, I've said before that like the design is not really part of the stream. So we're going to be making the design that I designed, and that's just the way it goes. I'm not a game designer, so I'm not going to teach game design on the stream. I couldn't even if I wanted to. So basically, the design is just the design that I have, and that's what we're going to do. But some people were concerned about the fact that I was saying that my design calls for the game to basically be a locked screen and you walk off just like the old Legend of Zelda. Now, I could defend my design decision to do that, I think, very well. I think about design things a lot. I'm not just an arbitrary person, and for people who think that that is not a good idea, I have plenty of things I would say to challenge that notion that you want to have a scrolling backdrop. But like I said, the design's not up for discussion, so I don't really want to get into that. But what I do want to do is say, if you are concerned because you would like to see how to implement scrolling, because maybe you have a game idea that would involve a scrolling backdrop, that is totally valid. And so what I would like to do as well while we are doing this is just show how there really is no difference between these two things, and that I'm just making basically a game design decision to keep this locked. But I will be able to show you, I think in just a couple days after we sort of finish our tile map exploration here, I'll be able to show you how to basically just turn on scrolling in a sense. Because scrolling, if you do the things that I want to do with the tile map, if you support all the things that I want to support, you get scrolling for free. won't be turning it on because I don't want it like in the game. But it's actually for free. And the reason that I say that is because I don't want there to ever be any loading screens or hiccups when you're playing this game. And what that means is that when you move, when the little yellow rectangle moves off the side of the screen, so if he comes down here to the bottom and he moves off the bottom of the screen onto the next screen, there's not allowed to be like a pause there or anything. It has to immediately show whatever that bottom screen is, right? And so I'm assuming that our engine will always be able to draw basically the screens that are all, the eight screens that surround the one screen that we're on. It would always be able to draw those at a moment's notice, right? Like instantaneously on the next frame. So if you wanted scrolling, it wouldn't really be a problem because all you would have to do is actually just go ahead and move the camera over and ask it to draw, part of that one tile map and part of the other tile map, and you could have a smoothly scrolling game with no problem. So I don't want anyone to think that our engine will be any cheesier because of the fact that it's not supporting scrolling. We will be doing no cheese. It is a cheese-free zone. But yeah, I just don't want scrolling because there's a number of things in the game design that I want that are specifically prohibited if you have scrolling. They won't work as well. And so I'm not going to do scrolling, but I will show you basically how to turn that on because if for some reason you're concerned about the technology, we are totally writing an engine that would have been able to scroll if it wanted to. I just don't want it to. So with that out of the way, let's talk about the next thing that I wanted to sort of get into here. So what I want to talk about now is I want to start talking about, we noticed we've got this to do in our code, which was math functions. I used a floor f function. And previously I used another function. I used sine to make the sine wave that we outputted. I don't know if you remember that, but basically up here at the top of handmade.cpp, when we were using our test sine wave, I was calling sinf to compute the sine of a value and that sort of thing as well. So really, I would like to finish up doing the Tilemap stuff right now, Monday, Tuesday, Wednesday, but really I think these things are sort of going to go hand in hand a little bit. And so what I would sort of like to do is just pause for a minute and talk about kind of all of the stuff that we're going to have to deal with and sort of the math function stuff as well, and how we're going to deal with that stuff. Because we're kind of getting into a part here where we're going to have math functions, or we're going to have a bunch of different things that we want to do. So here's the status. First of all, math.h is the C runtime library's include file. So this is something that ships with any version of C, right? It is the C runtime library include file that has a bunch of functions that you would need if you're going to be doing basic floating point mathematics operations. So I don't know if I can find a simple, I don't know if I can find a simple reference right here. Yeah, so this is an example of the functions that are in there, right? And they look like the kind of things that you had in high school trigonometry class, assuming that you have had high school trigonometry class. I don't know if there's some youngsters on the stream, then they may not have. But basically, they're the things that you would expect from there. Cosine, sine, tangent, arccosine, arcsine, arctangent, and arctangent 2. Now, arctangent 2 is a better way of computing arctangent, and we'll talk about that a little later in the stream. But basically, this is the inverse of the cosine, inverse of the sine, inverse of the tangent, inverse of the tangent in a different way. These are basically just the things that you recognize from trig. And we don't care about the hyperbolic ones, but again, they're the same as what you would find in mathematical textbooks. Similarly, coming in here, same sort of stuff you were used to in your high school math. You can exponentiate things. You can take the log base 2, log based, I don't know what these other ones are here, log base plus 1. Okay, so these are just shorthands for other ways of computing the logarithms. For convenience. There's the mod, which is basically the way of breaking a fractional number into its whole part and its fractional part. Raising something to a power, taking the square root. All of these things should be pretty familiar to you. Now, things that won't necessarily be familiar to you are these guys here, and these are some discrete math kinds of functions. These are the ceiling and the floor functions like that I was talking about before. The one that we used, that floor f, that I was using to sort of like move things to the next lower whole number on a number line. Those functions are discrete math functions to some degree and are not the kinds of things that you often talk about in high school math. Now, maybe some good high schools in good high school math talk about them, but certainly I don't think mine did. So these are some that you may not be familiar with, but a lot of them are very straightforward. Like I said, ceiling and floor are two that we were interested in and we talked about on the previous streams. But basically, those are all sort of implemented in there as well. Now, the interesting thing about this math.h file is these are all functions that would actually be implemented actually in the C runtime library calling a function. So for example, if we actually step in here, I guess I already had it running. If I actually step in here to, oh, is that function not getting called at all? That's odd. Don't you think that's a little odd? Why is that getting, how is that possible? What am I missing, folks? Did it not, oh, probably just didn't load the PDB as always. We're gonna have to fix that. I have a plan for fixing that, by the way. We'll talk about that separate. MSVC, Visual Studio, always the perennial thorn in our side, unfortunately. All right, so basically this floor function, if we go ahead and right click and hit go to disassembly, right? We can see what it's actually doing here. It's going to go ahead and it's going to actually call this floor F function, right? Which is in the C runtime library, and I don't actually know if I have that. It doesn't look like this is installed on the machine. I can't seem to find it. So I'm not exactly sure if we've even got it on here. But point being, this is actually the C runtimes function in here that does the floor, and you can see that it does a bunch of stuff, right? It's doing things, doing things, doing things, doing things, doing things, and so on, right? And that's to do this floor function, which, you know, is pretty expensive when we look at, look at all this stuff. It's doing tons and tons and tons and tons of stuff, and then it gets out here to actually get the result. So that's just a lot of work for this floor function. And remember, the only thing that we needed this floor function to do, the only thing that we wanted it to do, was basically produce the next lower whole number on the number line, right? The only thing that we actually wanted it to do on here, right, was if we were looking at the number line like this, right? All we wanted to do, we wanted that floor function to just drop us down to the next one, right? That's all we wanted it to do. And so what's kind of curious about this is it'd be interesting to know, right? Is there some way that we can go ahead and do that in a more efficient way that's just like simpler and doesn't involve using the C runtime library and you know, who knows what it's doing in there, right? Doing a bunch of stuff to comply with the C standard essentially, but we don't actually know if we need to comply with the C standard because there may be ways that we can do stuff entirely without that, right? And so one of the things that I kind of want to point out here is, actually I don't know if I need to open the Intel architecture reference manual just yet. One of the things that I want to point out here is that the Intel chips nowadays, anything that's going to be in a machine that we are going to be shipping on is going to have SSE2, right? That's basically an instruction set that, you know, for those of you who don't know, basically the processors on the Intel processors that are in all of the machines, like the one that I'm working on now, or anything that runs Windows pretty much, and anything that runs Mac OS X, and actually, I guess for that matter, the things that are in the PlayStation 4 and the Xbox One, for example. They are all running Intel-based architectures, and those Intel architectures get revised over time to have new instruction sets in them. So the instruction set that we're on right now is called x64, and x64 is basically a 64-bit version of the old x86 instruction set. It was made, I believe, by AMD, and that's why it's sometimes called AMD 64. And basically, it's just the basic set of instructions that we use to run code. That is what our code gets compiled down to. It's what, when we actually run this stuff, and I drop in here, and I go to disassembly, these are x64 instructions. That's what they are, right? So like move SS and call and CVT and blah, 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 blah. Those are all x64 instructions, but not every processor has the same set of x64 instructions because as the processors get revised over time, they add new instructions, right? And so they come up with names for these, like there's SSE, which is one set of instructions that all the chips will have nowadays. SSE2, right? There's even SSE, 4. There's AVX. So they keep adding newer and newer instructions, which basically add to the set of instructions that you can call, and oftentimes also add registers. So they add more registers to the processor that you can access, right? And so basically any CPU that we're going to target is going to have SSE2. Like pretty much everything that we could possibly hope to run on is going to have SSE2 at least. I don't remember exactly when it was introduced, but it's been around a long, long time. And so really, all of the SSE2 instructions, I don't know if we've got a good list of them here. I want to get a better list of these. Let me take a look. SSE2, MSDN. There we go. So if you take a look here at these, MSDN, if you search for MSDN and SSE and SSE2, they've got a little overview here where you can kind of pop down by various types of instructions. SSE, MMX was another one, a very old one, by the way, of instruction addition. That was on x86 as well. So these are the different instruction sets and sort of the instructions that we have available. And for SSE2, if I remember correctly, there's a bunch of instructions that actually allow you to do things. There's a number of things that you are able to do with these instructions that will probably let us just go ahead and do our own floor in a much simpler way. Now, like I said, I promised I would do everything from scratch on the stream, so that includes me having to dig through documentations because I never remember what the intrinsics are for stuff. I don't do SIMD programming often enough. I always have to go look them up. Whereas if you're a super SIMD, if you do SIMD every day, you just kind of know what they all are. So SSE instructions, I always have to look up. But basically, this is where I typically go first, right? I go to the MSDN page because they've got them kind of listed by what type of instruction they are. It's a little janky. I don't love these docs, but I don't know of a better set of docs where they're listed by type, unfortunately. Sometimes I look in the Intel Architecture Reference Manual, which also has some sections like that, but it's a little ugly, it's true. But anyway, if you go in here, you can click on things that talk about sort of what kinds of operations there are, and you can see, like, I'm going to click on arithmetic operations, right? And I'm going to make this a little bigger so we can actually see it in its entirety. So you can kind of see what all the instructions are that the processor has. It's got, add, subtract, multiply, square root, reciprocal square root, min, max, right? So it's got all these sorts of things. And so if you know that you have these, then obviously you can write things that use them. So the question is there anything in here that we could use essentially to floor, to floor our number? And the thing that I can't quite remember is whether or not, I don't remember if you have to go to SSE4 first, which I don't know if we want to necessarily be using. If you have to go to SSE4 before you can reliably do a floor in one instruction or not. I think maybe you have to or not. I'm not entirely certain. Anyway, point being, what we want to do is we want to look up in here how we would do, say, the floor instruction by using these intrinsics, and if we, and similarly, like, figure out how we would do sign and the other sorts of things we need to do using these intrinsics. And then what we'd want to do is we'd want to come back in here, and instead of using math.h, what we'd want to do is sort of introduce our own math.h, if that makes sense. We'd want to introduce our own sort of utility layer that for every platform that we care about, which is basically, it's basically just going to be ARM Neon, which is the instruction set for like mobile devices, and SSE2 for the most part, or maybe if we decide to do something higher than that, SSE4 or something like that, some version of x64, we'll basically make a thing that for each of the operations that we care about, like floor and like sign, we will go ahead and make our own implementation where we know what it does, and we know that it does only as much as we need it to do, right? And that it uses the most efficient processor operations to do that. And so that is where I would like to get to on that. Now, I don't know that we want to necessarily do that right now, but that is what we have to sort of drive towards. So that's one thing to think about. And by the way, I should also point out that sometimes, and I don't actually know if we can make this happen, sometimes you can also get the compiler to do some of this work for you if you don't want to do all of the stuff that I just said, if you basically turn on optimizations. So, for example, we are doing something where we have all of our optimizations turned off. We have -OD on our build line. So basically, we've turned off optimizations entirely. There's no optimizations that are allowed to happen. And so one thing that we could do is if we turn on optimizations, right? If I say -2, I think, I'm not sure I actually remember what the highest level is. We can double check. But if I turn that on, then it'll actually compile it with optimizations. And one of the things, well, so the first thing you notice is that I can't even set a breakpoint here because this function has almost certainly gotten inlined. So what I have to do is I have to actually go find where that floor real 32 to 32 actually happens. And I need to actually look there to see what the actual code does. So going into the disassembly and see if it does anything smarter. No, see, it still does floor, and there's nothing useful we can do about that. So I don't, sometimes you can set optimization levels where it says, don't worry about floating point consistency and stuff like this. I don't know. I'm not sure if there's a way to do it. Let's just double check to see if there's a way. MSVC, because I want to just point this out for people if they can. Someone on the stream will probably know. Fast floor F. I just want to know if there's any way to tell it to do a better version of that. Why did it link me here? I'm not sure. Yeah. Well, I don't know. We'll take a look. If someone on the stream knows, we can talk about it in the QFA, in the Q&A. But basically, like sometimes for certain intrinsics, there are compiler switches you can pass, or ways that you can tell it that you want to use that function. Like sometimes there's like a way to do like a built-in floor F. You'd call like a separate function, and it would know that it could do something that wasn't quite as direct or quite as comprehensive, for example. Yeah. So okay. So this is perfect. This is what I was looking at here. Floor has an implementation that uses streaming SIMD extensions too, which is what we were talking about, right? For information and restrictions about using the SSE2 implementation, see set SSE2 enable, right? Okay, so basically enables or disables the use of streaming extensions in the CRT math routines. Of course, we want to actually do this inlined. If you use OI generate intrinsic function compiler option to compile the project, it may appear that it has an effect. The compiler the authority uses intrinsic to replace CRT calls. That's good. That's what we wanted. So let's go ahead and try doing that /OI as well, just to see whether we can get it. I just want to see if I can show you this. I apologize if it takes a little while, but I really kind of wanted people to see the compiler doing two different things here, because there usually is a way to make it do it. No, why are you still doing that? Well, I don't know how to make the compiler suddenly do it. Anyway, point being, sometimes, maybe you know what, I could try calling something else, I suppose. I don't know. Sometimes you can get the compiler to do smart things where you can basically say, hey, look, I know that maybe it's not completely compliant with the C spec or something, but I would like you to go ahead and do it. Maybe I have to enable SSE2, but we're in x64 mode, so it knows that. I don't know. I do not know. Anyway, we'll have to ignore that for now, but please, if someone on the stream happens to know how to get the compiler to do some clever stuff, please mention it in the Q&A so I can show it. Basically, sometimes you can convince the compiler to start doing some of that stuff for you. I tend to not rely on that too much, only because, like you just saw, I never remember compiler switches, or even if I do, I don't necessarily know that the compiler can be trusted to do them and so on. So I tend to just like to take that out of the equation and actually have my own file where those will actually be called. So, essentially, what I want to do is start to think about these things like floor real 32 and round real 32, these sorts of things. What I want to do is I want these functions to eventually kind of migrate out into a math file where we can make the platform-specific versions that will do the right thing. And so I'm not sure exactly what I want to call that. Maybe I'll call that Handmade Intrinsics. .h, for example, and we will just move those into there for now. And really what we want to be able to do here is we want to be able to do more efficient stuff using whatever's available on the platform for each of these particular instructions. So that's something that we have to deal with, and we're going to have to deal with in a number of places. We're going to have to deal with it because we're going to need a sine function as well. We're going to need a cosine function, right? We're going to need a bunch of these things that you'll see over time. We're going to need an a tan 2. Tan 2 is usually y over x, isn't it, though? Sorry, just wanted to... Sorry to talk out loud here. Sometimes I get in the middle of something and I'm like, wait a minute. A tan 2 is usually not the way that I just typed it in, but you know how it is. Hello? It's usually written y over x. Yeah, that's what I thought. So I want to keep that same. Anyway, so point being, if you look at what the sort of stuff that we're going to have to do here is, we're probably going to have to spend a fair bit of time going through here and talking about how this stuff works at a lower level and implementing them based on each particular processor and so on. But for now, what we're essentially going to do is we're going to say, and you know what, and I can eliminate these to-dos for now by basically making just a giant to-do which says convert all of these to platform efficient versions and remove math.h. So basically what we're going to want to do is kind of come through here and do all of those that way. But that's going to take us a little bit of time because we're going to have to go through and look at how to implement things like sine because processors don't always have sine and you have to implement it yourself and so on. So for now, we're just going to call these guys here. But essentially what I want to do is make sure that our code isn't littered with calls to math.h. I want it to be calling into here so that we kind of can see all the stuff that we're using and off we go. All right. So the reason that I bring that up now is because of floor f, certainly, which we want to get rid of. But also there's another reason, a tan 2f, y, x, there we go. There's another reason I bring it up, which is that I wanted to start talking about trig and vectors because there's a bunch of things that we actually do need to talk about as well related to other stuff with our tilemap. Handmade intrinsics.h, there we go. Okay. So we need to do those math functions. But the other thing that I wanted to point out is, well, okay, there's a bunch of stuff that we're going to have to start talking about, like vectors and these sorts of things. And I got to introduce those concepts sort of over time. And that time is probably going to be pretty close, pretty soon. If it's not this week, that's probably going to be next week. What I want to introduce, though, just right off the bat, is when we're thinking about this tile map, there's a bunch of things that we want to do to it, but one of them is one that may not be sort of clear to anyone if they haven't actually gone through this process before themselves. And so rather than get all the way to the end of it and then show you that it's kind of unfortunate and have to sort of switch it all around and do it again, I'm going to kind of jump to a part in the implementation and show you what will happen so that you can kind of understand one reason why we need to think about it and so on. Yeah, basically, as much as possible, I will discover things on the stream for you in the natural way that they would get discovered. But sometimes I kind of have to head things off at the pass to prevent us from doing like a whole engine the wrong way and then coming back to it later and going, well, see, that's why you wouldn't do it this way. Sometimes I have to use experience and kind of talk about it earlier than it would normally come up. And so this is one of those cases. What I want to talk about now is I want to talk about basically the coordinate system that things are in. Now, what we've been doing so far when we made this tile map, right? When we made this actual tile map, I sort of showed you how to come at it from first principles, and we did a reasonable job of that. We've got it working right now. We can walk to multiple tile maps. It's fairly clean on the inside. There's nothing particularly odd going on. There's some stuff I said I wanted to kind of continue to push on, but for the moment, it's looking okay. But we've baked into here a very specific assumption. And one of those assumptions is that we're just dealing with pixels on the screen, right? Because basically everything that we did, you know, our tiles have a known pixel size. When we move things around, we're moving them in pixels and this sort of thing. What that means is if we were to change the resolution, right, of our screen, we would have to rewrite all of that code, essentially, right? I mean, let's say, for example, I mean, just for the sake of argument, because we could do this actually pretty easily here, and I'll show you what I mean. Let's say, for example, we came in here and we wanted to change the size of the tile map. So we were gonna change it from being 60 pixels across to being 30 pixels across, let's say, right? We just decided to change it. And so here we go. Oh, of course, and my guy's already stuck in the geometry there. I'm gonna have to move him a little bit over from where he is because he started off in the middle of the world. Hazards, ladies and gentlemen. Excuse me. So essentially, this is, you know, an example of what would happen if I go ahead and change that value so that now the tiles are not as large as they used to be. Instead of being 60, right, they're now 30. But, oh, and you'll notice the offset is wrong as well, right? Because the offset is one entire tile to that direction. So we should actually probably set these relative to the tile width, right? We should probably set them that way. Anyway, so here's our map again, right? And it looks roughly the same with a smaller thing, but what you'll notice is the guy now moves twice as fast, right? Relative to the size of the, of the stuff, right? Because his speed is in pixels. So if we change the resolution of the tiles, just the resolution of the imagery, right? It's as if the whole world has gotten smaller. Because everything that we're doing is effectively in some units, and those units are pixels, right? Now that's a perfectly normal thing to do, and like I showed you, it's what you would do if you move up each step and sort of, as you go, condense things down. Now the problem is you will never figure out that this is going to break something unless you try to run your game at multiple resolutions. And it's entirely possible that we would not really be trying to do that for quite some time. And so, like I said, what I'm doing today is, or what I'm doing right now essentially, is kind of forcing that issue and pointing out to you like, okay, let's start to think about the ability to change resolutions way easier than it may ever naturally come up or naturally occur to you. Because that's a very real problem, and we don't want to bake that assumption into our game, or we could create all kinds of headaches for ourselves by assuming that our units are pixels when pixels are just something that we use to display on the screen and don't really have any meaning in the game world necessarily. We should be able to double the resolution or have the resolution of our tiles in terms of graphics without the game changing at all, right? The game itself should play exactly the way that it plays. And so that's the first thing we need to think about, is the concept that units, there's such a thing as the units of our game, and those units may not be pixels and probably shouldn't be pixels. Okay, so that's one thing to think about. So that's thing one. And thing two that we need to think about is how our coordinate, so I'm basically trying to set us up to talk about the sort of the coordinate system of our game here. The other thing that we need to sort of think about here is, well, we know that pixels are one unit that we could be in, and there's reasons why we probably wouldn't do that. So that's one thing. But also, what direction do things go, right? If you think about it, this guy here, when he moves left to right, right, he's moving positive. We add numbers to him to move this way, right? So essentially, if you wanted to draw what our coordinate system looked like, right, you would say that x, the x-axis, it gets positive in that direction, right, on the screen. But what happens with y, right? Now, I don't know if you remember, but if we go down here and we take a look at what happens when the player presses the up button, right? If move up is down, then it's actually a subtraction that we do from the guy's y position. So really, when we're going upwards, we're subtracting, and we're going downwards, we're adding, right? And so if you think about it, that means that y, if this is the y-axis, y is positive that way and negative this way, right? So if this is the origin of our coordinate system, right, that's what it would look like. So again, there's an issue here. The issue may not be obvious, but it's one that I would like to demonstrate earlier rather than later, and that is that this is backwards from how all math is done, right? We are essentially doing something that is written in a coordinate system where it looks like this, and this is positive x, and this is positive y. But every math textbook that's ever been written in the history of time that I'm aware of, anyway, does have x positive going that way, but y positive goes up, right? This is how math looks, always, pretty much universally. And so if you're someone who's used to working with math, which you will be if you ever took high school math or anything like that, you will expect y to be going up, and all of the stuff that you do when you look at math textbooks and physics and everything else will be drawn this way. So, you know, it's y goes up, and angles are measured sort of starting going counterclockwise. They do not go clockwise, which is what they would do on this, right? You know, circles are drawn this way, and so on. So really, we have another problem. You know, we have our first problem is the pixels versus world units problem, right? But we have another problem, which is the upside down problem, which is the fact that our coordinate system currently is upside down from what math would want it to be. And there's no real reason in practice why you have to have your coordinate system agree with math's coordinate system. Okay, if you don't want to, you don't have to. There's no compelling reason, there's no objective truth to what direction y has to go, right? But I can simply say from experience that you will save yourself a lot of headaches if you are constantly looking at your math textbook and seeing this, and then you can go type something in and it is that over in your game world as well. Because otherwise you're constantly having to deal with this inversion that occurs between what you see in a math textbook when you're trying to do something or looking up something advanced math-wise, and what you actually go ahead and do on the screen. For example, if we wanted to shoot a projectile at a particular angle, let's say, you know, we've got a particular theta and we want to shoot a projectile off at that angle, right? We would know, and we'll be talking about this a lot more, so if you don't know, that's fine too. There's cosine and a sine of that angle will give us the x and y of the vector that we need to sort of shoot it off in that direction. Well, if you're thinking about it in this way, and you're looking at your math textbook and trying to learn from it this way, and then you go and implement it, and your dude is always shooting you know, the other way. It's like, oh, he's shooting down instead of up. What's going on? I'm totally confused, right? And then you're just like, oh, right, my coordinate system is backwards. And the more complex your equations get, the easier it is to forget in there somewhere that there's an upside downness and wonder why stuff isn't working and why it's subtly wrong. So I would say that we have two problems that we probably want to fix. We want to fix the pixels versus world units, and we want to fix the upside down. And I wanted to just kind of introduce those now that we're sort of a little ways into it, because those are things that just from experience, I can say we probably don't want to bake into our engine, because we're probably going to be sad if we do so. And there is no real obvious compelling reason why you have to do either of these two things. But just like I said, if you want to make your game support multi-resolutions and you want to have an easier time going from math textbooks to your game and vice versa, it's just they're good things to do. And so I'm going to do them in our code base for those two reasons. But your game would work just fine without them. If you didn't ever care about changing the resolution, or you want to do some hacks to change the resolution, and so on, and if you didn't ever care about going back and forth to math textbooks, then you wouldn't ever have to worry about that. Okay, so where does that leave us? Where indeed? It leaves us with 15 minutes. I've been talking a lot tonight. There's been a lot of blabbing. I've been a blabbermouth, it's true. But where does that leave us? It leaves us at the point where we kind of have to start to think about this Tilemap thing a little more robustly, like trying to just make this a little cleaner. You know, gotta do a little stretching today. I gotta go stretch. After the stream's over, we're stretching. It's gonna be stretching time. Maybe we could do one of those group calisthenic things where, like, I do the stretch and all of you guys do the stretch as well, and then it's like, you know, it's like group calisthenics. Yeah. Anyway, so we got to start thinking about all these things. We got to start thinking about tile maps. So there's a couple things that I still want to do that will naturally fall out of the things that we're doing, but those two that I introduced today are things that wouldn't, I don't think, have naturally fallen out. They would have been things that we would have to get to later and then realize were busted and then be upset, right? And so I'm just trying to kind of save us that that sort of grief by pointing them out ahead of time because I've been there already and know that these things go poorly. So now that we've got that out of the way, what I would like to propose, first of all, is having some notion, just to start off with, having some notion, therefore, of what the units are in the world, right? I'd like to have some notion, I'd like to be able to tie this back, basically, to an actual notion of how big things are in the real world. And the reason I want to use real world units, essentially, is because I feel like if I use real world units, it's easier for me to conceptualize how big things should be, and I can play with that if I want to. But like, for example, if we want to implement something that has gravity, we know how fast gravity is in the real world. So if we already have real world units everywhere for stuff, then it's easier to just type in the value for gravity and be starting at something that's realistic, and then you can tune it from there, rather than having no idea what would be realistic and having to guess and then tuning from there, right? So given that, what I'm thinking about here is basically like, okay, so we know our guy, right? We know that our person is basically going to be about one, you know, I'm looking at this, I'm imagining how big he's going to be. So I'm imagining that we want the player to be, you know, something like that size, something like that rectangular size. I don't know exactly, but something like it. And so if we think about, you know, I don't know how wide a human is across, right? You know, I mean, I feel like one of these tiles, for example, is probably not a full meter across. Maybe it's a meter across. I don't know. It's hard to say. But I would basically think that, you know, if we were to ballpark the size of the guy, you know, what we could say, here's what we could say. Here's one way I could ballpark sort of roughly what we might want those units to be. Let's say I open up Google here and I say, let's say our dude, you know, he's a little kid. So I don't know, let's say, what's the average height of, let's say, you know, a 10-year-old? The average height of a 10-year-old boy was 55.2 inches. So let's just say, randomly, 55.2 inches times, excuse me, sorry, in meters, how big would that be? 52.2 inches in meters. So that's 1.4 meters, right? There you go, 1.4 meters. So how big am I? Let's actually see. 6 feet in meters. I'm 1.8. So 1.4 would roughly be, you know, sort of the height of one of the, you know, what one side of these, let's say, would be 1.4 meters, something like that. So if a tile on a side was 1.4 meters, we could actually use that value as sort of a calibration value to say roughly how big these things actually are supposed to be in real world units, right? We could come in here and say our world definition, we actually have a thing which is going to be 1.4, right? Which is meter, you know, tile side in meters or something like this, right? And so when we create the world, we're just going to say that the tile side, you know, one side of a tile measured in meters. I'm just going to say for now that that's about 1.4, right? That's about, it's 1.4 meters on the side of a tile. So if we wanted to measure now in the world how long something was, we could actually do it in real world, you know, in meters or something like that. Now, I'm not sure if that's exactly right. You know, we're going to sort of say that that's roughly it for now. Okay. So what that essentially means is if a tile is that big in meters, right? And then we also have, right, over here, and, you know, I guess we could also say, I think let's go ahead and say definitively that our tile side is going to be square as well, because I know that I want square tiles. So let's go ahead and say a tile side in pixels, right, which we also have, which kind of forms this tile side in pixels. And I guess that should actually be a UN32, since we can't we're not going to allow there to be a fractional pixels there. So tile side in pixels on the screen is going to be 60 for now. Now, you may want to let it be fractional. You might think, okay, why not let it be a fractional number of pixels on the screen for a particular tile? And the reason that I don't really want to do that is because if you think about it, we would like the art for the game to line up properly with the pixels on the screen. When we get to the renderer, you'll see why we may want to do that to avoid basically having more blurriness introduced than necessary and more filtering introduced than necessary. So you may wonder why I'm actually doing this as an integer for now, but I think I want to do that for now. We'll see. If we could always decide later that we don't want to do that later on, but for now I think I'm going to stick with that. So basically the tile side in pixels is going to replace this width and height here, and this will now give us an idea of the real world size of things and how big they should be on the screen. And with those two, we can now do a mapping that will allow us to write things like the player position, right? We can write something like the player position in a way that will actually tell us something more interesting than just how many pixels he's moved. We can say how many meters per second he's going, for example, or things like that. And then we can always map him back into where he should be in the world afterwards. Okay, so I'm going to go ahead and fix the stuff here. I'm going to change tile width to, because we got rid of that tile width to tile height, so we have to change tile width to tile side in pixels. Go ahead and change that everywhere that it was being used. And similarly, we have to change tile height to tile side in pixels as well. So okay. Let's see here. What did I do incorrectly? Unary minus applied to unsigned type. Oh, whoops, sorry. I can certainly make that a signed type. No need to be overzealous there. Word chooser inversion from int to real 32. Is the upper left x is a real. So I will go ahead and make that a real as well. And it looks like that is, yes, there we go. Okay. All right. So I think that's basically everything, and it looks like everything is still working properly there. No oddities. Everything still seems correct. So that's fine. And now what I want to do is go ahead and start to make, well, I don't know if I'll quite start this yet. Maybe we'll do it tomorrow. But what I want to do is continue down the road of kind of cleaning up this tilemap stuff. Now that we have a notion of what those two things are, I don't quite necessarily want to use them yet because there's something that I think maybe we'll do one step of the tilemap compression first that we haven't quite finished yet, and then we will come back to it. So I think I got time to do this in 7 minutes left. Well, actually, we started 5 minutes late, so technically we've got about 12 minutes left. So we're going to do these, and I'll actually put it to do here. To do begin using tile side in meters. Okay. So what I'd like to do here is basically say, looking at these two things and thinking about them a bit, I think I mentioned on the previous stream, because we were right in the middle of working with them, I mentioned that I didn't really love, and I have this to do here. These are still in pixels. This kind of was the foreshadowing of the thing that we were kind of introduced here. So I know that these things I kind of don't want to be in pixels anymore for canonical positions. I already kind of said that. So I want to start moving to real world units for our offsets. But you notice we have these two numbers here. We've got the tilemap x, the tilemap y, and the tile x and the tile y, right? So what can we say about these values? I was saying before that, like, I've got this raw position. The raw position was basically a tilemap x and y, which is some index into which of the tilemap portions we're having. Remember, just to give you a refresher, just for folks who, maybe forgot from last stream, we've got, this is the setup that we've got here, right? We have a game board, a game board that currently looks like this, right? You saw me walking around it earlier on the stream. All right. There we go. So basically, you saw us walking around this, right? This is a tile map, this is a tile map, and so on. And we had made coordinates for these. We'd said like this was 0, 0, this was 1, 0, this was 0, 1, and this was 1, 1, right, for the tile map that we were on. And then inside there, we had additional things where each tile was numerated as well with a coordinate system, right? We kind of kept doing all these numberings. And so what I wanted to do is I wanted to say, because this is something that I saw as we were working on it, but we didn't have time to do it last time. What I want to do here is I want to say, why do we need two separate sets of indices, right? Why do I need the tile map x and y and the tile x, tile y, right? Since I know already, right, that we're going to have a fixed number per tile map there. And even if we weren't, let's put that aside for a second. Why can't I just have an integer for all the tiles in the world, right? Just, one integer for all the tiles in the world. So one integer for x, one integer for y. And then whichever tile map you're in is basically just looking at that value and taking off, say, the high bits of it, right? It's just looking at whatever the high order part of it is, right? Does that make sense? So, to map a tile x or a tile y into a particular tile map, basically all we're doing is we're sort of saying, okay, let's go ahead and page. I mean, really what I'm saying is, let's make a virtual memory system for our tile maps. Let's just have a single 32-bit value for the x and a single 32-bit value for the y that is the individual tile. And all the tiles in the world, so we have 4 billion by 4 billion is the maximum size we could support, which seems like a pretty reasonable size to support at maximum. Right, that's, what did we say our size was? 1.4 meters. So 1.4 meters times 4 billion, right, is that many meters. So that many meters, I guess I'll copy that, circumference of the Earth in meters. So that's the circumference of the Earth. Well, actually, let's see here. Can I get that in kilometers? So figure 40 million meters if we were to walk all the way around the Earth. And this is how many meters we could support, which is more than that. So we can basically support an entire Earth's worth of geometry, which seems like plenty for our purposes. So if we do a 32-bit x and a 32-bit y, right, what I'm basically saying is, let's go ahead and imagine that 32 bits is broken up into, pieces of some kind, like chunks, basically, right? Where we basically say, okay, let's say the bottom 4 bits, right? So that's 16 or something. The bottom 4 bits and the top 28 bits or something like that are going to be separated in these numbers. And the bottom 4 bits will tell us where in a chunk we are, right? And the top ones will tell us where in the tile map, when the indices of the tile map we are. So this part tells us the tile map index, and this part will tell us which tile we are in a particular tile map, right? Basically what I'm doing is I'm packing the two numbers that we had before into one number and just segregating it by the bit amount, right? Now you're going to say, when you first see this, you're going to be like, wait a minute, Casey, though, how is that going to work? Because if you remember what we did before when we were drawing a tile map, right, on the screen, we basically had tile map count x, tile map count y that said how big these tile maps are. It was 17 by 9. And there's ain't no way you're going to get some number of bits down here to be 17, right? They're either going to be 16 or 32, and there ain't going to be no 9 that's going to be either 8 or 16. So what gives, right? And that's a totally valid question to ask me. I'm very glad you did. How did I scroll like that? I don't know what happened there. I'm very glad you did. What I'm basically proposing is that we no longer think about the screen that is being displayed as the tile map. The tile map is just going to be a chunk that we can reference and store, but a screen will just be a view that could be viewing multiple tile maps at once, right? So for example, if our tile maps are 16 by 16, right, then basically we will have one tile map that covers essentially this much, of our displayed area, and then another one that covers that much or whatever. And when we look at a screen, we'll just reference two tile maps, right? No big deal. Very, very straightforward. So that's essentially what I would like to do, is make it so that we can go ahead and do that sort of packing, if that makes sense. So all right, if we've run out of time for today, then this may be the time when I've done the least of, no, I guess one other time I talked basically for the entire stream. I was going to say this may be the stream where we got the least actual programming done, but I was trying to explain to you what we were actually going to do. So okay, I'm just going to say that one more time so that tomorrow we can basically start directly on it. So what we want to do, now that we've talked all about all of this stuff quite a bit, is I want to basically take these values and I want to collapse them into one, right? So what I want to do tomorrow is I want to say, take the tile map x and y and the tile x and y and pack them into single 32-bit values for x and y, where there is some low bits for the tile index and the high bits are the tile page, right? And basically what we're doing here is we're constructing essentially a virtual memory system, exactly like the kind that you would see for just regular memory, only instead of it being a 1D thing like memory is, it's 2D. We're basically just making a 2D virtual memory system, right? All we're doing is we're saying we have some gigantic world, right, that's 4 billion by 4 billion across, right? And we want to break that up into chunks, right? And I'm thinking those chunks maybe will be 16 by 16, maybe they'll be 64 by 64, who knows? We'll talk about the reasons to make different sizes. But basically we'll break those into chunks, and those chunks will be something like 16 by 16. And then whatever we want our game's display to be, however big we want it to be in tiles, we'll just grab out that portion of it and display that as the tile map. So instead of the screen and the storage being the same, we're just going to split those up into two pages. And again, you may ask, why don't I just store a giant 4 billion by 4 billion array for my tiles? Well, that's too much. It's too large. 4 billion times 4 billion would never fit in memory, not even close. It would be absolutely massive. So what we're going to do instead is we're only going to, and we'll show how to do this later, as soon as we get this stuff working, we can actually go ahead and do the stuff for the storage. But basically what we're going to do is we're only going to store the places where the world actually exists. So as the world kind of snakes its way through various pieces, we're only going to store pages where there's actually data, and that way it'll be nice and sparse, and we won't have to store a 4 billion by 4 billion world, which of course you could never actually store. Okay. So I want to do that and turn it into a paging thing. So that's one. I think we'll be able to do that tomorrow. That'll probably take the whole day tomorrow, but we could probably do that tomorrow. And then the next step, because of the things that I've talked about earlier today, is we got to fix these tile relative things. So we're going to compress those two guys down, but then these tile relative things, what I want these guys to be, right, is I want these guys to be, convert these to math-friendly, resolution-independent representations of world units relative to a tile, right? And so basically these are going to be, now they're going to be in those units that we talked about before, which is the tile side in pixels. So basically what we're going to do is we're going to convert these canonical positions over to something that's nice and clean. It can be used as a virtual index into a giant tile store that stores as much space as we want for tile maps. We're going to be able to do a nice sort of, math-friendly, resolution-independent movement of things relative to the tiles, so that'll all work nice. And then we can also get rid of this raw position because, again, we won't ever have to think again about things in terms of those pixels the way that we were, so we'll just store everything as the canonical positions, and we'll get rid of these. And that will make our tile map, that will start to get our tile map into really good shape, something that we can really start to think about being sort of a quality system that we're going to be able to use. And again, what we will do too down here, again, instead of this thing looping over a tile map, this thing will actually just loop over tiles and pull the tiles out of that sort of virtual store once we build it. So that is what we'll do tomorrow, but without taking up too much more time from the Q&A, I will close this And I will say, let us go to the Q&A here. If you could, please prefix your questions with Q:, and keep them to things that we've done today or on previous days. Because if you want to ask questions about sort of off-topic stuff, you can always do that by coming to earlier in the stream, basically before the scheduled start time, like 8 p.m. If you come at like 7:45, I am usually on the stream early and I field questions about whatever you want. But during the official Q&As, I like to keep it on topic as much as possible. Let's see. Will we be making a map editor? Not really, because this is a procedurally generated game. So you can't really have a map editor if you have to generate everything procedurally. Let's see. To fast floor, were you talking about I equals int fp if I greater than fp I minus minus? Well, so not really, like, well, so let me show you, first of all, sort of, this is not necessarily what I'm thinking about for fast floor, but let me see if I can show you. There's a store instruction that I was thinking of in SSE4 as well that would be sort of the one-step way to do it. So, excuse me. Let's see. Oops, I wanted floor, not ceiling. So in SSE4, which I don't know if we should use or not, because I'm not sure how many machines have SSE4. I don't know what kind of coverage we get. But basically, if you there's this round PS function that actually can do all 4 different types of rounding. Let me see if it's got the documentation for that here. It's kind of slow. It's kind of pokey. Flog them hamsters. Flog them. All the hamsters on the Azure cloud right now. Run. Run faster. Okay, there we go. So if you take a look at this instruction that's in SSE4, this is when, if we had SSE4, I'd just use it. So when I was saying about SSE2, I was thinking more like, okay, what are we going to cobble together to make it work relatively well in SSE2? But, you know, point being, because we could do like fraction extraction or there's stuff we can do. Anyway, ignoring that for a second, this is like the Uber example of what I wanted. You can do an round PS, and that will basically take floating point values and it will round them using whatever mode you want, right? And so you can do all sorts of nice rounding with that. You can do a floor, right? You can do a seal, you can do truncation, you can do rounding, and you can say whether you want it to go towards negative infinity or positive infinity, right? So you can construct the round that you actually wanted to be a floor, to be a ceiling, or to be whatever. So that's like the perfect instruction. That's the one you wish that they would have just had to begin with, but unfortunately never did. So what I wanted to know was basically, what is the shortest set of SSE2 instructions that I could do to emulate that for our purposes? Now, it turns out that actually we can do something a little bit more clever that I was going to get that will eliminate the need for floor in this particular case, and I'll add a thing here. We can actually just use truncate for our purposes, because once we have this stuff packed, we won't need negative offsets anymore. So it's a little anticlimactic either way, but we probably will need floor for other things as well. So point being, I'd like to go through and get a good feel for what's the easiest way to do an SSE2, into bucket thing. And, I might have to ask some folks who are better at SSE stuff, because I forget it. I page it in when I do SSE, and then I page it out immediately, and I forget what they are. I'll have to study up. Recursive anomaly. Have you considered only storing the changes made and then just regenerating everything else from seed instead of storing it all? So that's an interesting... So what you're talking about is... So let me talk a little about that, because that's actually an interesting question. So what he's basically asking or she, I suppose. I guess I don't know the gender of anyone. What the questioner is asking is, you know, do we have to actually store everything, or can we generate stuff from seed values, right? And so when we go into a new page, when we go into a new part of the world, can we just generate it from seed and then recompress it? And I believe Minecraft works that way. And then just recompresses and stores the world that after you change it. It only stores blocks if you change them. I don't know. There's games that work that way. And there's two reasons why I don't like that solution. The first reason I don't like that solution is I feel like it generates worlds that are kind of boring. Like, worlds that can be generated per page by a seed look like they were generated per page by a seed. And so I am more interested in creating worlds that are a lot more creative than that and involve things that would be much too expensive to create in a way that will allow you to create them from a seed on a page basis without an extraordinary amount of work. So I don't think I want it for that reason. But there's another reason I don't like that idea. And the reason that I don't like that idea is because I don't actually think that it's a good... it doesn't have performance leveling characteristics. Which is to say that, let's say that you're like, oh, well, I can be more efficient by just not ever storing this. And then when someone comes in here and if the world gets modified in some way, then I'll write it back out only if that happens, right? The thing that I don't like very much about that is what optimization is that really doing? Assuming that the user does go through and do lots of changes to the world, then you end up back in the state that you would have been if you were just storing it, right? And so I'm not sure where the benefit comes. If it's just to sort of spread computation time out, then maybe that's something. But in general, it doesn't really save you any space if you assume the case where the user goes around doing as much stuff as they can to the world, right? So I don't see it being really that big of a win, or even a win at all, really. It's sort of something that only saves space in the case of a world that the user isn't touching a lot of. Which again, you know, isn't perhaps quite so interesting. So Sean McGrath suggests doing fp:/fast, which is let's take a look here. Remember, I was asking earlier on the stream. I was like, can we get this guy to start outputting for that floor instruction? I kind of wanted him to output a better thing for floor than it was outputting, and I felt like the compiler could have been doing a better job. But when we actually went and looked, as you can see, it's still calling floor. There's the call to floor right there. So what I was hoping to do is basically to make it so that we could have the compiler output something a little more sensible than this stuff that it is outputting at the moment. And so the commenter is suggesting to do fp:/fast, first of all. Let's see if that works. See if that has any effect there. Go to disassembly. Okay. Let's see. There it is. Yes. Yes, 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 yes. This is what we wanted. This is much better. Now you notice we are not getting any more floors. Yes, thank you. fp:/fast. Remember I was saying there's a way to like tell it not to have floating point consistency. So let's take a look at that. That is the thing that we wanted right there. Fast. Thank you, stream. It's so nice having a stream. You could just ask a question, and you don't have to go digging through the documentation. So on MSVC's compiler, here is the way that you tell it not to worry about adhering to the C++ standard as much. Okay. Improves the consistency of floating point tests for equality and inequality by disabling optimizations that could change the precision of floating point calculations. That's the precise one. And that's what it was on before, right? Fast allows it to relax the rules for computations so that it can do like things that might be less correct or less accurate in the case of certain exceptional circumstances. It will just ignore those sorts of things, right? And that's what we wanted, because I knew that I only needed to do the floor, basically the standard usage of floor, just the basic concept of floor. I didn't need it to handle, all sorts of special things like, I don't know, denormal numbers or who knows. I didn't need it to handle all the things that the C++ spec may say that it needed to handle. And so I was hoping that I could get it to go ahead and generate a fast floor, because I know that I don't have any weird special requirements. I don't have to adhere to the C spec. I just need a basic floor function. And so that FP fast is exactly what we needed to have that happen. And so that's pretty awesome. In fact, I wonder if that also will do the right thing for some of the other functions. Like if I said something like here, if I say y equals sine, you know, something like x, I don't know. Let's take a look at what it does there. I just want to see if I can, what it would generate for other sorts of stuff. Let's take a look. Let's take a look. So it'll still generate the call to sine. So yeah, so that may not help us much. Let's take a look. Yeah. So, you know, 6 to 1/2 doesn't know the other. You know, we still got, it's better than nothing. We're going to have to do some work still, but it's good to know that we can get it to do some of that stuff for us. So that's pretty good. I'm gonna leave that in a rem there, optimization switches, just so we can remember that and don't have to look it up again. Thank you, Sean McGrath. I noticed the math library, all of the placeholder functions are in the form int result equals foo, return result. What's the reason for making it that way instead of just return foo? So I believe what the person is asking is, when I went and made the intrinsics here, why am I doing it, why does it look like result equals something, return result, instead of just making it be return the thing directly, right? Why isn't it just return atan to f, y, x? Like, why isn't it that? The reason is very mundane, but I think it's still useful. It's for debugging, is basically it. So let me show you what I mean. Let's say, for example, that I was to do it the other way, like I do it like this, right? So there we have our floor function. It is now operating kind of in the way that you were asking about. And when I come in here, I'm in this function and I want to see what it actually computed. What was the result that it computed? And I hit F10. And you'll notice I can't see it anywhere. I can't see the actual value. Now sometimes, depending on the circumstances, you can use, where is it here, locals. You can use this locals thing to basically say what is the result, if that makes sense. No, it's not locals. Sorry, it's auto. Sorry, I almost never use these, so I'm a little behind on whether it's autos. Sorry. So sometimes you can use, it depends on the debugger. Sometimes you can use this autos thing. It will show you what the return value is here, right? And so sometimes you can do that. But sometimes the debugger gets confused and doesn't show you that. And also there's some debuggers that don't have that, depending on what platform you're on, right? And so if you don't have that, a debugger that has that capability, then basically what I do is I just always write it to look like this, so that if you were to end up on the final line of that function, you always have a convenient variable you can just type into a watch window, and it's always result as well. So I usually always name things result so that I can just leave result in the watch window, and it's essentially always shows me the return value of everything. That is just a convenient way to make sure that no matter what debugger you're on, if it can do anything at all, you should still be able to see what the actual computed value is. So that is why I do that. It doesn't cost you anything, because as soon as optimization's on at all, any compiler will trivially optimize this out, so you're not wasting any computing power here at all. It's free. It's one of the few things that really is truly free. And so, you know, it's just a good thing to do for convenience. Isn't it a little preemptive to be drilling down on intrinsics this early in development? Doesn't that kind of go against your ratcheting process? Not really, because we're not supposed to be using any libraries. So as soon as we start using something, it's time to sort of take a look at it. So again, I didn't do it before we started taking a look at it, but we are using them. And so the time to look at things on the stream is when we start using them. And so this is kind of a thing that shouldn't really be allowed, this map.h. And so it's time for us to start taking a look at those at this point. Now, we'll be able to sort of skirt it a little bit because we can actually get rid of the flooring function, like I said, using because of the way that we're going to refactor stuff. But we're going to be wanting sine and cosine real soon. And so the time for us to actually have to deal with this stuff is actually fairly soon. So it doesn't go against my ratcheting process. If I could push them out to later, I would. But the bottom line is we have to call them. And so floor f we can actually get rid of, but sine f and cosine f we're going to need, and we're going to need them soon. So. Is tile relative for the real 32 coordinates better than tile page relative? So I am thinking, I mean, my assumption, I mean, I guess the answer is sort of, I'm not sure. I guess what I would say is I don't really know that it matters which one we pick. I think they might both roughly be the same. But I suspect that it's just easier to do it tile relative to the tile, because relative to the tile is always uniform everywhere, whereas relative to the tile map would not be. Like, I mean, well, I don't know. I guess what I would say to that is I don't know. I don't know which one of those would be better. I can't think of a reason offhand why you couldn't do either one. I can't think of a reason why you couldn't just use either of the two. Yeah. So tile page relative may be better, or tile relative may be better. Tile map page. Okay, so one reason we maybe would want to think about using it being relative to the page would be because if we do things on page boundaries, like say, sort of collision-y things, maybe that I don't know. I really don't know. Like I said, I haven't written tile map games before. Most of the stuff that I write is like full 3D or whatever. So, you know, it's a little bit of an exploratory process for me this time around. I'm not qualified to say definitively, yes, you should do it this way, or no, you should do it the other way. So I don't know. That's a very good question, and I don't know which answer is better. If we're lucky, we'll see as we start to do one that it either is nice or isn't nice, and isn't nice in a way that would be better if we switched, and then we could switch. But I don't know offhand. Why not just store the player XY coordinates in world coordinates and determine which tile map and tile he's in by dividing modding? So the reason for that is just float precision. I covered this actually on a previous stream, so you might want to go check it out. Basically, you can't, a single floating point value, 32-bit floating point value, is not enough precision to actually store 256 bits of fractional per pixel plus the amount of size of the world that we wanted. We wanted to potentially have like hundreds, if not thousands, of tile maps of screens across in the longest case. I mean, probably realistically we'll never get up to thousands, but we at least wanted hundreds. Thousands might be too long for the player to ever get from one side to the other, right? But we definitely wanted to be able to do a thing where there might be 100 tall set of rooms that you might go through or whatever. and floating point precision isn't sufficient. And I showed that on a previous stream. So we definitely don't want to do that. So we need to have basically a two-tiered system so that we can have more than 32 bits worth of addressing for the guy in terms of where he is. Let's see. You mentioned in your picture that the last 4 bits could represent the tile in the map, and the top 28 would be the tile map location, but since we plan on making the tile map sparse, we won't need that many bits to represent that. Why not use the bits for tiles? So I think maybe you are thinking I'm saying something different than what I'm saying. So here's what I'm saying. Let's draw this out a little more explicitly. I should really learn to just make a grid. Wow, this is a very warpy grid. So let's say that each of these things, right? 1, 2, 3, 4, 5, 6, 7, 8. One, 2, 3, 4, 5, 6, 7, 8. Let's say that each of these is 8 by 8, right? So each of these little things here is 8 by 8. And we want to store it sparsely. So our world occupies, this region, right? So it occupies this area, okay? That's where there actually is world. But there's collision everywhere, so the player can't get outside of this area. This is the only maps he could ever get to. So what we want to do is we want to store this stuff, into our magical machine that we're going to make here for storing the tile set of the world, for storing the tile map. So we know that it's trivial to store just a regular old tile map. We've done it already, right? We have all the code in here for storing a tile map that's just one screen's worth of tiles or whatever. So we know we could store an 8 by 8 tile set trivially. We already saw how to do that. It's not very hard, right? But the question is, what do we then do to store the rest of these guys, right? We need to be able to have a bigger sort of addressing scheme to talk about where this guy is, such that a specific tile in here has an address that is, whatever he is in his 8 by 8. Inside this 8 by 8, he may be the tile 3, 2, right? But we also want to talk about the fact that on the world, he's, whatever he is here, 0, 1. So he's 3, 1, right? And so all I'm talking about is the address for this guy, for this tile right here, X and Y, right? If it's 8 by 8, we need 3 bits for the tile address, right? So 1, 2, 3, right? So this right here is the divider, and we have 3 bits, right? Into those 3 bits, for the X we would put the 3, right? And for the Y we would put the 2, into here and here, right? That's the location of the tile inside the tile map. And then for the location of the tile map itself, we use the top bits, right? Which is 32 minus 3, right? Which is the 29 bits here, right? 29 bits, 29 bits. We would put 3 and 1. We'd put 3 in here and 1 in here, right? Now we have a universal way of addressing this tile such that we know what part of it is the tile map inside, which is inside a particular 8 by 8 tile map that's stored densely, and then another one that's for storing which tile map he's in sparsely. And then what we need to do, and we haven't done this yet, what we need to do is have a way of taking this top part here, this 3, 1, and looking that up in some kind of sparse way so that we don't store absolutely everything in the entire map, right? So, but that's all I'm saying. Do you know of the Intel Intrinsics Guide? It's interactive, which makes for easy filtering for instruction set and categories. No, I didn't. That sounds pretty awesome. Intel Intrinsics Guide. Oh, wow. That is spiffy. Of course, it seems to be a little slow. Okay, there it goes. Wow. Okay, that's pretty cool. Thank you very much, Flying Sand. That is great. Okay, so this is something we should totally bookmark. I will add that to the forum site as well. That's great. That's really nice. So that's pretty cool. You can just go ahead and say, what's the instruction sets that you are going to target? And then it only shows you, oh wow, that's awesome. That's just great. Wow, that makes life a lot easier. And then you can just see all the instructions that are there. That's great. Thank you very much. Is there a reason we have a majority of the code we've been working on in handmade.cpp and not something like world.cpp or tilemap.cpp and player.cpp? Yes, the reason is because that's premature. So we will have more files, but only once we determine what the architecture correctly actually is. So for example, right now, we're starting to get the tilemap stuff straightened out. As soon as the tilemap stuff API-wise, I'm satisfied with it, which I'm not yet, because I talked about 3 things today that I want to do to it. As soon as that's ready, then we will be pulling it out into its own file where we can consider it kind of done for a while, or at least where it'll just kind of reside. But I don't like to pull things out until we're sure that they're correctly consolidated. Because otherwise, you're just presupposing you know what the API boundary is between things, and that's a bad idea. You never want to presuppose you know what the API boundary is. So you always want to start by just writing whatever comes to mind in the place that it's most easy to write it, and then once you are satisfied that it's correct, then you pull it out. That's almost always the best way to go. So Willstorm asks, are we going to move the origin to the bottom left? Yes, we will probably move the origin to the bottom left to get, this is when I was talking about getting rid of the floor. So I'll talk about that a little bit once we do it, because that's an easy way to get rid of the floor problem. Shift drag for straight lines. Okay. Is that a tip for these? For this? Does that work? Let's see. That does not work. That just draws a circle. That doesn't. Look at what you've done. Oh, how do I? That just changes the size of the brush. That does not work. I think you have to be in line drawing mode, probably. Yeah. Yeah, you have to be in line drawing mode, which I'm too lazy to switch to line drawing mode. I gotta have my quick dashing. They should have some kind of function that lets you draw a straight line even in freestyle mode. Will you be able to find ARM assembler instructions to match the Intel ones you are specifying if when you want to port to ARM? Yeah, so ARM Neon is pretty good. It won't probably be one-to-one. The instruction set on ARM Neon. The instruction set on ARM has this thing called Neon, which is basically like the equivalent of SSE. So it's like that, but for ARM for the ARM processors. And I don't know. I have docs for it on my other machine, and I'm sure you can download them usually here. I don't know if they have them on here. I don't know if there's what the right place to look them up is. But basically, there's a bunch of the equivalent things to all the SSE instructions. Neon typically has something suitable for doing whatever you were doing in SSE on the ARM architecture as well. I don't know if it has. It probably doesn't necessarily have that rounding. Well, it might. I don't remember. I did some Neon programming a while back, and I remember it being very good. So I would basically say that most of the time you can probably find something as good or better sometimes than you have in SSE with Neon. So that's what we'll be porting to on ARM, if we choose to port to ARM. How are we going to deal with different types of tiles? So basically right now, this is just a placeholder. So on our tile map, we just have an uint32 that's a tile type. But what we will do in the future is once we actually decide, once we're actually working on the game mechanics part of the game, it should be free, essentially, for us to change whatever this is into some more elaborate structure that has all the stuff that we might want for a tile. But it's very premature to think about that now. So all we really need to do now is know that we can store something. And then we can assume later that we can change into storing whatever it is that we actually wanted. But right now I just picked a uint32 because that allows us to store some type field basically that we can use to draw something so that we can actually see what we're doing until we actually know what we want for our tiles. All right, it looks like we are done with questions. Thank you very much for joining me for another episode of Handmade Hero. I'm sorry I talked so much today. There was kind of just a bunch of stuff, I think, maybe from thinking over the weekend. Sometimes the brain is going. So I had some stuff that I wanted to talk about. So anyway, but I think we are on good track anyway. By the end of this week, I think we should have all of our tile stuff straightened out. I think all the things that I wanted to do will probably be well and truly done. So that is a good thing. And basically what I would, I guess what I'd like to do is I'd like to get to that point by the end of the week where we can say that our tile map stuff is sort of where we want it to be. And also maybe throw a monster in there, throw another thing in the world so we can have two things in the world moving around, the player and some other thing, just to set us up for next week when we start to work on some of the other stuff, like, you know, how we're going to treat entities and animation and stuff like that, because obviously that's another big part of the engine architecture. So we want to kind of get some zygote stuff in there. We want to try to get some stuff in there where we're playing around with it so we have some idea of how we want that stuff to work and what we want the engine to do as far as animation's concerned and those sorts of things, because those are the sorts of things that can be kind of tricky. So thank you very much for joining me. If you would like to follow along at home with the source code, you can go to handmadehero.org and go hit the little pre-order button. If you pre-order the game, you will get access to the source code, and every night it sends you a link basically that every night you can download the source code. I upload it immediately after we finish coding. So if you want to do that, you can do that. If you'd like to support the video series, we have a Patreon you subscribe to that's on this little Patreon button. And we also have a news and forum site that you can go to if you are trying to learn along with Handmade Hero. It's got the schedule for the week on here. It's got an episode guide for catching up on past episodes with time-coded access to the videos and stuff that helps a ton. There's a coding resources page that has ports and things like this, as well as reference materials. So if you're trying to follow along on a Mac and you need some help getting the platform stuff up and running, that's a great place to go. Same with Linux. And then also we have forums where you can ask questions, code discussion, forum that you can ask questions about the code that we are doing and get help from people in the community. And I also read them all, so I'll come in there and answer stuff when I see something that I can answer. So definitely check it out if you're learning along with the series. It's a great place to go, and it has a lot of really helpful information on it. So again, thank you everyone for joining me for another episode of Handmade Hero. It has been a pleasure, and I hope to see you all here tomorrow at 8 p.m. Pacific Standard Time again, when I'll go through and do that virtualization of the tilemap stuff that we talked about tonight. And maybe if it goes well, I don't know if it does, but if it goes well, then I can also do the relative sort of world unit stuff that I want to do. If not, we'll do it on Wednesday. So thank you everybody for joining me, and I hope to see you tomorrow. Thanks everyone.